Hello everyone, welcome back to MLC. This is lecture 8. Today we're going to talk more about what are the common properties and techniques we're going to use in MLC machine learning compilation for specialized accelerators. In the last lecture, we talked about how to build MLC flow for a GPU environment, and in the past lectures, we talked about how to do so for CPU environment. And one of the things that we haven't touched upon so far is, when we start to look at recent hardware trend, we can find that there are a lot more specialization going on. So traditionally, if we look at the hardware programs that we normally write, we typically write program in a way which we'll call scalar computing, where we just need to specify for loops and compute how do we get each element of the corresponding data. And then as the modern hardware evolves, we start to introduce what we call vector computing unit. In these cases, there are instructions that allows us to take a vector of certain lengths, and we will be able to perform, say, 4 floating points additions and multiplication together. And that is the foundation of a lot of the modern CPU architectures, and gives us a lot of accelerations in some of applications. And more immediately, we start to see a specialization trend among the hardware backends, especially for machine learning. This is because the machine learning computing brings such a high demand, and the traditional hardware themselves, it's really hard for them to keep up with all those demands. So we start to see a trend of specialized accelerators. In particular, there are accelerator designed especially for machine learning, like Google's TPU, or in other cases, GPUs and even CPU themselves also start to introduce some of those specialized acceleration unit, like NVIDIA introduces Tensor Core, and AMD more recently brings what we call matrix core that allows us to do matrix multiplication in a single instruction. So all those common hardware trends brings a common pattern on the hardware specialization. Especially most of the instructions that those hardware provide involve the element called tensor computing. So traditionally, when we load a element from a memory, usually you just need to load one element. Now in the regime of tensor computing, usually there are instructions that loads data in a very bulk fashion, so you can load a region of data onto your memory. And there will be instruction that takes regions of specialized data and run accelerated computations, like there will be matrix multiplication instruction, or sometimes even efficient convolution instruction. So one more question we want to ask, how can we build a machine learning compilation process for these kind of specialized hardware? And one interesting thing about those specialization hardware is that each kind of hardware is different. So if you look at one hardware backend, it may contain a 6x6, 16x16 matrix multiplication instruction, and the DMA unit allows you to shuffle in, say, data in the unit of 1024. If you look at another hardware, the specific instruction can be different. For example, in certain cases like CPU, more recently there's a dot product instruction that allows you to take two vectors and make dot product, and the ability that we build to support these different kind of hardware backends also differ. And that makes the MLC process quite challenging in general. Okay, so today we are not going to work on a specific kind of specialized hardware because most of them are not openly available. Instead, what we're going to do is we're going to study some of the common properties of those specialized hardware programming. And those properties are going to be applicable if you are going to build a MLC backend for a particular hardware, and they are being applied to they will apply to build some of the backend, for example, for TVM themselves to support some of the specialized hardware backend. Of course, the things that we're talking about today are not going to be comprehensive, so it's only going to, but it's going to touch a lot of the key elements that's going to be useful to a lot of hardware backend. So to begin with, we're going to come back to a low-level NumPy code to help us understand what are the key elements of a specialized code that we write to target a specialized hardware. In this particular case, we are making a simple assumption of the specialized hardware model. So this particular hardware contains several key components. I'm going to walk you through the code themselves. This particular code, of course, is implemented in Python. It can be run in Python or structured in a way such that we can easily also map it to a possible code that runs on an accelerator. So first thing that you might notice is that in this case we are working on computing a transposed matrix multiplication, which means that my outcome Cij equals sum over k aik times bik. So effectively C equals A times B transpose in here. So if we look at the code here, you can find that it's slightly different from the original low-level NumPy code that we write. Right? So first of all, we are allocating 3 temporal memories. Of course, in those cases, this temporal memory sits on it's a normal NumPy array, but let's assume that these 3 pieces of memory sits on a specialized part of the system. For example, the C accumulator is a specialized memory that accumulates the result of matrix multiplication, and A reg and B reg represent the 2 input registers or 2 input special memory that this matrix multiplication unit takes and do the matrix multiplication and then do the accumulation. So in this case, this hypothetical acceleration unit contains a specific instruction called accel tmm add, which does accelerated matrix computation. Right? So effectively what it do is it will take a slice of accumulator matrix C and run matrix multiplication of A and B transpose and add it back onto the slice of accelerated matrix C. And this means that in order for us to leverage this to do a bigger matrix multiplication, in this case, let's assume that we are doing 1024 matrix multiplication. So A's input is 1024 times 1024. What we need to do is we need to divide the computations onto sub-matrix computation, right? So effectively, if this is my big matrix, I'm going to divide it into a sub-matrix computation in 16 by 16 fashion. And each of the time, we are going to copy a sub-matrix from 16 by 16 sub-matrix from A, and another 16 by 16 sub-matrix from B, and in this case, this is actually B transpose in here. And we're going to run this matrix multiplication in here. So let's look at each of the lines in here. First of all, there's this line called ACL DMA copy. So this resembles a typical memory copy operations the accelerator will do that moves the memory from the left-hand side to the right-hand side. So effectively, in this case, we are moving a 16 by 16 matrix onto a register here. Similarly, the DMA copy here moves a 16 by 16 matrix from B to B register in here. And finally, after we move those data onto registers, the next thing we're going to do is we're going to do a TMM add, right? So in this case, we are taking the data from A register and B register and accumulating that, run matrix multiplications and accumulating that onto C accumulators. We're going to do that for 64 runs because each of them computes a sub-matrix computation of 16 by 16. So after we do that for 64 runs, the C accumulator already contains the result of the 16 by 16 sub-matrix that we are interested in. And then we are going to copy the data back onto the global memory that we have in here. And this picture help us to summarize the overall flowing pattern of the data, right? So effectively, we are taking the A and B, from normal memory that you have, we are going to do DMA copy, that copy the data onto those special registers. And this is where this matrix multiplication addition operation happens, right? So in this case, we are doing TMM add in here. And finally, we are doing in DMA back onto the global memory. So if you look at this code and try to digest a bit of what are the common elements in here, you can find that usually if you start to write code that involves special accelerators, it involves several elements. First of all, it will involve special memory scopes. In this case, C accumulator, A register, and B register, of course, we are writing them in NumPy because NumPy don't have special memory scopes, but they correspond to effectively they correspond to special regions in the hardware. For example, they could directly correspond to a fast register file in the hardware, and that allows us to copy data in and store the intermediate data during computation. The second element that we're going to have is the specialized instructions, right? TMM add. So this is an instruction that allows us to accelerate, in this case, matrix multiplication, transpose matrix multiplication operations. But there's also a special requirement of such instruction. Normally, you cannot arbitrarily take a piece of, say, data from a global memory, accelerate that. You have to place data onto a special region of the hardware so that this data exactly feed onto the acceleration unit. That is why we need to copy the data explicitly to A rack and B rack before we run the TMM. And finally, there are memory copy operations, right, that allows us to copy the data in a bulk fashion from a global region to some of the local registers and local specialized memory. These specialized instructions also interleaves with the additional loops. So in this case, actually, we still have some flexibility to how to order the computations, right? For example, we will be able to, in this case, reorder I and J, and that's still a valid computation for building a 1024 and 1024 matrix multiplication. So even in the regions of specialized accelerators, there are still, especially in those that are programmable, there are still a lot of flexibilities we can do on optimizing some of the outer loops to coordinate the computation, and as also making it a general purpose enough so that we can not only build an accelerator for matrix multiplication, but also make it work for things like convolutions and dialectic convolutions and other operations. Okay, so this is one example of low-level NumPy code for a hypothetical specialized accelerator model. And actually, this kind of model usually reflects accurately a lot of the challenges that we're going to face in programming some of the domain-specific accelerators. Okay, and of course, we can go and run the code to confirm that actually the code that we build for the low-level NumPy specialized low-level NumPy version of this transpose matrix multiplication matches this overall computation. So now we've introduced a low-level NumPy code. Next, we are going to think about how we can bring in some of the insights to design mlc abstractions, to design compiler abstraction that allows us to be able to represent some of the structures that we have in the specialized acceleration computation. In particular, one of the things we find out is that in most of the computations we see in the low-level NumPy code, they happen in a bulk fashion, right? So we have instruction to copy a region of data onto another region. We have an instruction to take data from specialized memory and do matrix multiplication. And all those instructions and all those operations are carried out by taking a subregion of tensors and combining that with another subregion of tensor and running some computations and store that back onto some piece of specialized memory. So one of the key things here is what we call a tensorized computation that allows us to be able to present a tensor computation that takes a region of tensor, work with region of tensor as a basic unit of computation, right? And we want to combine that with loops. In the case of Tensor-IR, originally when we talk about Tensor-IRs, we usually talk about a block that contains a piece of code that tells you how do you compute each element of the target instances. And actually, in order to look at special accelerators, it's no longer true that each of this basic operation step is one element at a time. So we want to be able to have an operation that allows us to represent not only an element at a time, but also a bulk regions of element at a time. So in order to do that, we're going to introduce another tensor code here, which most of the element of this tensor actually you have already seen them. The main difference here is that you can find there's already a for loop of 60 by 64 by 64 by 64, and we have a tensor block in here. And in this block, what you'll find is that this block contains 3 block iterators. Still, the relations are SSR, spatial, and reduction. But each of the steps in this particular block computes a subregion of the target result. So if this is my final matrix, and each of the block here, TMM 16 by 16, computes a 16 by 16 matrix multiplication substep, right? In a sense, that's still a reduction. So we want to take 16 by 16 by 16 matrix multiplication and add that back onto the C subregions. And you can find that this block still kind of closely follows the original block that we did for scalar computations. And within the block, there are also intermediate subblocks, right? So if you look at this block, you can find that they have an initialization region that specifies for the first time of reduction how do we initialize the corresponding data point. And effectively, this is the implementation that iterates over 16 by 16 regions and set that to 0. Similarly, this part represents, during reduction steps, at each step, how do you perform the updates to a subregion of the result. In this case, this subregion is C, right? So why do we need to have this block abstraction at a tensorized computation level? The reason is that a lot of those computations will be mapped onto the specialized hardware. For example, this particular computation, we're not going to compile that into a for loop, but in the case of, if we already have an instruction that directly perform 16 by 16 by 16 matrix multiplications, we can directly replace this piece of code with an instruction that perform that operation, right? So effectively, it allows us to group those tensorized computation together for easy targeting of specialized hardware. And of course, we can use tvmscript.show that allows us to see the corresponding IR module. One thing that you might notice is that on the block signatures, it contains analysis of the read and write regions that this block does. For example, in this case, the TMM 16 by 16 reads from 16 by 16 region from A and B, and it writes onto a 16 by 16 region of C. This information is helpful for us to perform analysis when we're transforming the block, especially loops outside. So one of the key property of the block is try to provide some kind of isolation, so that from outside block point of view, what all it does is it will read from that 16 by 16 region and writes onto a 16 by 16 region by C, and all those contents are implementation of that. But when we are transforming the loops outside, actually we can completely rely on information of read and write information to perform some of the writing. So it helps us to isolate from the outside and inside. Why this kind of isolation is important? The reason is that if we have this isolation, I can feel free to say replace this with Excel TMM add in here, and still perform a lot of the transformations that we have, right? Because from outside point of view, it doesn't matter within the block body whether it's an accelerated instruction or it is or it is a normal for loop, as long as the interfaces matches each other. Okay, so we'll be able to run the code and confirm that actually this block code can give you the correct result. Another thing that we can do is, we can also run transformations around those blocks, just like the transformations we did for a block that computes a scalar computation. So in this case, what we can do is we can, create a schedule, get the block, get the surrounding loops along that block, and we can say do the split and run a reordering here. And you'll find that effectively the resulting code will have something that contains exactly the original block's implementation. So the block body does not have to change when you change the loops in the outside. But we'll create additional loops in the outside, reorder them, right? And then there will be a clear remapping of the iterators that help us to maintain the invariance that allows us to effectively carry out internal computation. So this gives a lot of advantages in a sense that, we can still specify, for example, how do we want to compute and accelerate the internal blocks, while still gives our MLC system, the outer system, ability to be able to iterate and search over possible loop ordering and other optimization patterns in the outside. Of course, in most of the cases, we do not start with a Tensor-AI that contains a tensorized block, because if you take a high-level computation, say a computational graph from PyTorch or TensorFlow, the first step usually we will generate a for loop like this, right? That is really plain vanilla that loops over each of the iterators, and you just use it to do to do reduction, to do matrix multiplication operations. One of the things we can do though is that we can also transform this piece of code to bring up a block during scheduling or during optimization. So the following code tries to effectively split out the 16 by 16 iterators from the original matml code, reorder them so that we have outer loop and inner loop, where the inner loop contains 16 by 16 by 16, right? So if we do that, we can find out it reorganizes this data, contains 16 by 16 loops in the inside. And what we can do is we can try to cut these loops and trying to bring this 16 by 16 by 16 iterations together. So effectively, we want to be able to bring in a new block that contains this region here. And we can do that through a construct called blockrise. And if you go and call blockrise, you will find that it creates 16 by 16 by 16. It creates internal blocks that reads from a 16 by 16 by 16 regions from the A's input and B, and writes from those 6, right? So this is exactly the code that we manually wrote in the last part. So that is a way for us to be able to transform the original code and try to bring that onto some of our blocking structure that we have. And this blocking structure allows us to create effective mappings onto the accelerated hardware. And these are common mechanisms, right? So in a lot of cases, when we have existing programs that sit in high level that do not have those block structures, and we have a hardware that requires this kind of blocking structure so that we can match some of the tensor computations onto low-level hardware, then the MLC system will either take a program and perform automatic or semi-automatic transformations that help us to bring the state to our final part. Of course, after we bring the data onto this part, we have talked about our low-level NumPy code. There are other elements besides the tensorized computation. We still need to be able to introduce specialized memory scopes that we can map to onto the special registers or memory regions in our specialized accelerator. So in here, we are creating 2 additional stages called A register, B register, and global accumulator, and put them onto the original computation. So in this case, you can find that we created additional data computing memory, right? So we have, A rack, B rack, and accumulator. And we have copy stages in here that copies the data from A to A global register, B to B global register, and then copy the data back from the accumulator onto the global memory. And this is our computing block in here that carries out the computation. So this code roughly can be represents the overall computing structure that we wrote in a low-level NumPy. Right? And in this case, when we look at this scope in here, so these are what we call memory scopes. There is a special tag in the compiler that allows us to be able to recognize that in the follow-up backend creation phase, map this piece of memory to that special tag. And we are following a convention here where global try to mark what is the relation of the memory with respect to thread hierarchy. In this case, because we don't have any threads in here, A, B, and C are both visible to all the threads effectively. And the second part, A register, B register, and accumulator are called tags. So this tags marks what kind of special memory they do. Of course, right now they don't resemble any meanings, but the compiler backend will be able to match those things and say, this allocation should be translated onto a register in the A register or B register. So they closely resemble what real-world special accelerators behavior. Okay. So now that we have those specialized memory scopes, that's the second element. One of the last elements that we need to do is we need to be able to map some of those tensorized computations. Right now, the body of those computations are still in for loops. We want to be able to map them onto lower level implementation that can map to, say, assembly code of my accelerated accelerators or other implementations of these accelerated instructions. So in order to do that, this is a process, by the way, called tensorization. So if you worked on vector processor before, you might heard about the process called vectorization. So vectorization is a process that tries to take code written in for loop scalar form and try to transform them to leverage the vector processors that we have. So you will be able to perform, say, like a vector add and vector modifications and so on. So it's a transformation step that allows you to take the original code that works on scalars and move them on to work on tensorized computations. Similarly, the tensorization step effectively is a way for us to move a subregion of code that was originally described in a scalar form, and I want to remap them onto another code that effectively runs tensorized computation. In order to do that, one of the challenges that we will face is that each of the hardware is different, right? So there's one hardware that might perform 16 by 16 matrix multiplication, and you might find another hardware that performs a 16 by 16 matrix vector product. So in some sense, it's really duplicated effort if you want to go and build a specialized MLC backend for each type of hardware. So instead, in the tensorization process, what we do is we will try to register a pairs of functions which we call tensor intrinsics. So in this case, we want to register two functions. The first function is a description function. So this is a tensor function that describes for existing accelerated subregions what do we do. So in this case, this tensor piece describes for existing region, we are going to read from a 16 by 16 regions, right, and write on to 16 by 16 region in C, and it's working effectively. This piece of code describes semantics of that accelerated instruction, which is make sure multiplication and add things back onto that piece of memory. We also have another function that tries to describe the implementation. So what it tries to do is says that for a given buffer here, we want to be able to describe what is the actual code implementation that implements that piece of code. So in this case, we are trying to call onto what we call action function called tmm16. So it is a microkernel that we write to accelerate the 16 by 16 matrix multiplication. We can also change it to other form of code, like emit calls onto inline assembly and other cases. So this is a final code that we want to place as a target. And we want to register it as a tensor intrinsic, both containing a description and implementation. So our tensorization process will try to, take a subregion, right? Try to look it up from a description part to match, to say, hey, does this part of the computation matches up my description? If they do, we're going to go and replace that with the implementation part. If you look at the description implementation, you can find that they also contain several interesting elements. Right? So in this case, the scopes tries to show the special memory scopes that we are looking for. So effectively, this implementation only works, and both the description and implementation actually all mark scopes, right? The scopes marks that okay, this particular tensor intrinsic only works for input memory from A global registers, B global register, and writes on to accumulators. It also gives you a few low-level constraints in here. For example, there's offset factor that says that my underlying memory have to align to multiple of 16 in here. And there are also in this case, in the implementation side, it tries to do what we call stride matching. So the stride matching effectively allows us to be able to have a stride buffer in this case. So that means that this particular piece of A can be a submatrix in here, and the strides effectively represents the regions in here, so that when we're accessing the piece of memory, it can be non-continuous in here. So if it's a 16 by 16 memory in here, and our result is 1024 by 1024, then the strides here equals 1024. So that for us to visit the first element, the second row of element, we know that we can add it by the length of 1024. And in this case, match buffer directly constructs, effectively it says that I'm expecting a input buffer of size 16 by 16, and I'm going to store the result strides onto this variable sc in here. Okay, so in this implementation, what it effectively does is to call onto action function by passing in what we call access pointers. So these pointers are the starting pointer of A, B, and C in the void opaque form. We're also going to pass in the strides onto the resulting function, so that it can perform computation on sub-slices of memory. In other cases, we might expect memories that are compact, that do not come with strides. In these cases, we also need to create special requirements of a low-level validation to validate whether or not some of the compacting requirement is fulfilled. Okay, so as a preparation step, we still need to decompose reduction. In this case, we want to decompose our reduction step that contains an initialization that fills all the elements to 0, and then an update step that runs the matrix multiplication and addition step, which we aim to replace with our target instruction here. Then what we can do is we can tensorize with the tensor intrinsic name, and after we do that, we can run sure again. And what you can find is that effectively this piece of tensorized computation body get replaced by a call extend step that calls on to an external function, and these intrinsic are slightly longer, so they effectively these access pointers correspond to the access pointers of A and B and C, and then there are additional parameters that are passing to a lower level. So in this case, we are using call external to call into external function in Xylem environment. The downstream compilation can easily map this onto an instruction that implements the operation. For example, I'm going to give you a specific implementation in this case. What we're going to do is we're going to simply build this TMM 16 by 16 by writing this following C code that implements that piece of what we call microkernel, right? So microkernel implements that 16 by 16 matrix multiplication. In reality, of course, we can write embedded assembly code and other forms that directly correspond to acceleration code. So it effectively demonstrates a mechanism that enables us to try out different kind of things. And we're going to combine that with the original piece of code through what we call import LVM. So effectively, we import temporal LVM module onto my final kernel. And we can try go and build and run it. And you'll find that actually gives you the correct answer. So in this case, we have run all those transformations. Of course, this particular experiment still runs on CPU. So the global.arack, global.brack, and the SIG accumulators in this case translate onto CPU memory because we do not run any of the specialized mapping paths and map them onto specialized memories. And the particular acceleration function also still runs on CPU. But the same mechanism allows us to use those transformations to map those tensorized computation bodies and other computations onto specialized acceleration instructions. We also released optional material that for you to go and try out on how do we leverage similar mechanisms onto mapping the set of computations onto NVIDIA's Tensor Core. That's a real specialized, there's a real GPU that comes with a special acceleration unit. There are also other additional topics that we do not handle so far that you are more than welcome to check out in the future, including things like layout constraints and interaction with thread hierarchies. But this lecture have already covered some of the key ideas and key elements, specifically how we can group the tensorized computation onto subregions and leverage those key construct called blocks that allows us to run transformations of tensorized programs and map some of the regions onto the specialized implementation that Howard can take. Okay, with that, I would like to conclude today's lecture, and thanks everybody for coming, and I will see you next week.